In this video, we're going to look at autonomous second-order differential equations, and we're going to explore phase planes. We're going to start with a warm-up of a first-order ODE of the form x prime is equal to f of x of t, where the solution of x of t can be interpreted as a description of the motion of a particle on the line, on the real number line. If x prime of t is equal to x of t squared minus 1, we want to find our equilibrium points and graph the phase lines. Now, as before, what we do is we draw our vertical axis as our dependent x of t. So this is a x of t. Now, if I were to take x squared minus 1 is equal to 0, we know this factors into x minus 1 and x plus 1. If right here is 0, right here is positive 1, and right here is negative 1, then we'd have a graph that looks something like this. Now we can see on this graph, which is basically if I were to take the regular XY axis and rotate it 90 degrees, that this would be positive, this would be negative, and this would be positive. So we know in this phase line that since these are positive, they will be moving away from that equilibrium point, moving vertical, north, away from, but in the north direction or straight up. Because the ones in the middle are straight down, then it's, well, negative. It would be having its movement would be like this on the phase line. Straight down, south, vertically going down. And then, of course, because this region is positive, it would be looking like this. So we know that this is stable, and this is unstable. And we know that unstable is a source. And we know that stable is a sink. Just as a reminder when we did these before. Now, when we look at our warm-up, it was of order 1, first order. It was homogeneous because we can set this thing equal to 0. It's autonomous. It doesn't depend on t. Nonlinear because of the x squared. It's separable because we can divide both sides by x squared minus 1 to solve. Ordinary differential equation. We can put this in a lot of buckets. We're able to graph the behavior of the line on the real numbers. What if we have a second order homogeneous autonomous ODE? How would the graph of its behavior look? Well, we graph it in R2, and then we have it of the form x double prime of t is a function of x of t and its first derivative. So if this equation for the following existence and uniqueness theorem holds, that's kind of important. So here is, given the initial value problem, where I have x double prime of t is a function of the original function and its first derivative. We have an initial value for x. We have an initial value for x prime. The partial derivative of f with respect to x and the partial derivative of x with respect to x are both continuous, and that should be x prime there, on a continuous region where x of t is between a and b and x prime of t is between c and d. In the xt x prime of t plane, containing this point x naught y naught, then there exists a unique solution of differential equation at the point x naught y naught. And the solution is continuous on the interval t naught minus epsilon and t naught plus epsilon. This goes back to our calculus when we did the epsilon delta proofs for some epsilon greater than 0. Because we don't know how big this interval will be, we'll use numerical methods like we did in section 2.6 to approximate the solution. However, we can graph these on the xt x prime of t plane to get an idea of the behavior of the solutions, just as a slope field was for the first order ODE. For an autonomous second order differential equation where x double prime of t is equal to f of x of t, x prime of t, the xt x prime of t plane is called the phase plane. Solutions in this plane are plotted in two-dimensional curves. where x of t, x prime of t, t naught is less than or equal to t, which is less than or equal to t max. And we know from calculus to how to find the tangent vectors to these parametric curves at any given point in the plane, which is why we have to have Calc 3 before this class. In the phase plane, the tangent vectors at a point are tangent vector of tittle, that's a tittle, x tittle t, x tittle prime t is equal to x tittle t in the I direction, x prime of t prime in the j direction. What? So in other words, what I have is x prime of t in the I plus the function evaluated at the x of t, x prime of t in the j direction. For an autonomous second-order differential equation, a set of tangent vectors drawn at the grid of points is also called the phase plane. We call this a vector field, and we'll learn about that in our Calc 4 class this quarter for this differential equation. A phase plane with a vector field and a set of solutions curved drawn on it showing how solutions looked in various regions of the plane is called a phase portrait. When using a computer program, x prime of t is equal to y and y prime is equal to f of xy are used, and we say that the trajectory is the moving along the solution curve. If the graph is a circular trajectory, then the solutions are periodic. So it looks like this or like this, depending on the rotation. If the trajectories have a spiral inward, then the solution approaches a stable node as t goes to 0. Think of a dampening system. Doesn't matter if I start and go clockwise or counterclockwise. I'm still going toward the origin. If the graph has trajectories that spiral outward as t goes to infinity, then the solution will be unstable. Think of resonance. So it doesn't matter if we're going clockwise or counterclockwise as we spiral outward. If the graph has trajectories that both spiral inward and outward, then the solutions are semi-stable, and these are called saddle points. We're going to explore this more in the next chapter. For the phase plane, x prime of t, x double prime of t, x prime of t of 1 minus x squared of t plus x of t is equal to 0. Find the phase plane and interpret those solutions. I would like you to go here to figure out what this phase plane would look like. Now, what I need to do is I need to figure out, based on the GeoAlgebra, how to type this in. I'm going to let x prime of t, equal y. That means this equation then becomes x double prime of t plus y, 1 minus x squared plus x is equal to 0. That means the second equation I need to put in for y double prime of t, which would be equal to negative y, 1 minus x squared minus x. Now I want to show you what this looks like, so I'm just going to go grab that. And here's what the graph looks like. Notice what I put in for x prime of t, I chose y, and y prime of t, which is solving for x double prime of t, would be this. And we see now let's just take a look at this picture. We see, depending on what we choose here, some of the initial values will spiral into the origin, and so they'll be dampening. Others, if I chose this as being my initial value, it's going to spiral outward. And I know the way it's going to spiral based on my arrows. See my arrows here? So it depends on what you are choosing, whether you're going to spiral inward or outwards. So I would either have dampening, or head toward the origin, or have resonance, which I spiral outward. Now, we're going to talk a little bit about pendulums. I'm just going to move that up and out of the way. A simple pendulum consists of a bob and a mass m of mass m. Here's my bob of mass m, suspended by a rigid weightless wire of length L. The pendulum is free to swing back and forth in a plane. Using vector calculus and Newton's second law, following the equation can be derived for the angle theta of t between the wire and the vertical axis at any given time. ML theta prime of t plus CL theta prime of t plus mg, where it's mass times gravity, the sine of theta t, is equal to 0. Where C is the dampening coefficient and g is a gravitational constant. Find the phase plane for this and interpret the solutions based on the results. So once again, I'm going to go to my GeoAlgebra. Now, for this, what I'm going to put in, like I did before, is I have to do a replacement for theta prime of t. So I'd say theta prime of t, which when I'm using GeoAlgebra, that's my x prime of t, if you will, which I'm going to let it be y. That means my theta of t is equal to x. That means theta double prime of t for this equation is going to be negative cy minus 3, the sine of t. I'm going to go out to GeoAlgebra and I'm going to put that information in. Of course, I have to use A for GeoAlgebra, and this is what it looks like. Now, you have to know a little bit. You have to make a decision about what your A would be. Here's an example of what A would be as 0. Now, notice when A is 0, this portion of the graph is periodic. And then these seem to be moving. I don't know. I can't really tell if it looks like it's spiraling or not. It just looks like it's moving in this general direction. Now, if I were to have chosen this and moved it a little bit differently, if I were to say I want to get it closer, what we're going to see is that it could spiral in. It could also spiral out. Just depends on what your C value. I chose a C, or in this case A. So we named it A because it requires it to be A. Being 0 on this is what it looks like. So let's go take a look at my next one. So again, what I'd like you to do is I would like you to go to GeoAlgebra and try putting these in. Your replacement is x prime of t is going to be y, and then your x double prime of t is going to be 0.8 y plus the sine of x. So that's what you're going to put in for that one, and I want you to take a look at what that looks like. And this other one, this would be x prime of t is equal to y double prime of t, which is what they put as y prime. This is y prime on this website, would be equal to a negative 3y plus x cubed. And this one, again, y is equal to x prime of t. That means y double prime, which is equal to x double prime of t, or y of t, y prime, not y double prime, which would be equal to negative 3y. Oh, okay. And then this would be plus x of x minus x cubed. So go ahead and go out there and take a look at that. And we'll discuss those in class. I just want to let you know that this first one up here that I didn't graph for you is going to be dependent on where you're standing. We're going to have one in which it spirals in. So if we look at my phase plane for this one, depending on what your initial value is, some of them are going to spiral inward, and then some of them are going to do this kind of thing. So it just depends on what you choose. I know that's poorly drawn, not as good as if you were able to go into GeoAlgebra. This one, by the way, it has this kind of asymptotic behavior. So it just depends on where you are. This one seems to come in and go like this. And then this one comes in and seems to go in like this too. And this one seems to come in and go in like this. If we're starting down here, it comes in and goes like this. It comes in and goes like this. And this one comes in and goes like that. It's kind of what the graph looks like. And then for this last one, it's really kind of funky. And again, I probably should go out and take those pictures. But I'm going to let you all do that. This one kind of does this. It comes in, kind of does this, kind of crosses, and then comes back out and does this kind of weird shape. And then this comes in like this, kind of makes like almost like a K. This seems to look like this. This seems to look like that. Really, again, depending on what you are choosing for your initial value when you're out there in GeoGebra. But I do have this lovely symmetry, though, so that's kind of nice. Like something like that. Go out and play with those. And that's it for this video.